So the first thing we want to know is what kinds of linear transformations should we expect to be invertible? So how are we going to be able to tell when a linear transformation has an inverse and when a linear transformation might not have an inverse? So real quickly, an example of a linear transformation that might not have an inverse might be something like this, right? Where most of the points in my codomain did not come from some point in my domain. Right? If I choose a bunch of different points in my domain, I'm only getting codomain points that are lying along some proper subset of the codomain. So we can't have an invertible linear transformation here because most of the vectors that I could choose in my codomain are not outputs from this function. And so we're not going to be able to define a linear transformation that goes backwards from the codomain to the domain. Another problem would arise from the fact that there are potentially two different vectors that give me the same output. So two different inputs that give me the same output from my function. Let me see if I can figure out how that works. Here we go. So here's two vectors, 0, 4 and -1, 5, that are different vectors in the domain, but their outputs are the same vector in the codomain. That also presents a problem from the point of view of finding an inverse, because an inverse is supposed to exactly undo whatever the original transformation did. But I can't undo it if two different inputs are giving me the same output, because then if I tried to feed that output back into an inverse, it would have two different outputs. And actually, in the case of linear algebra, infinitely many different outputs, which is something that we can't abide for something to be called a function. For an inverse function to exist, we need for every output of the original to have been associated with one and only one input from the original domain. And so we cannot have a function that's not injective. We also can't have a function that's not surjective. So in order to have an inverse at all, we need to be assured that our original linear transformation is both injective and surjective. It needs to be a bijective linear transformation so that it represents a one-to-one correspondence between all the points of the domain and all the points in the codomain. And that means we can go both ways, and that means we can undo whatever the original transformation does. So the big question for us then is, how can we tell what kinds of linear transformations are going to even have inverses? How do we tell when a linear transformation is injective? How do we tell when a linear transformation is surjective? And of course, the biggest, most fun one of all, how do we tell when a linear transformation is both injective and surjective? So the first activity of the day is just going to get us back into the material from the last couple of classes. We have here 9 different properties of a linear transformation from n-dimensional domain into an m-dimensional codomain, and its standard matrix is called A. So here's 9 different statements, and what you and your team need to do over the course of the next 10 minutes is figure out which ones of these statements. I would say first maybe look for the ones that tell us that the associated transformation is surjective. So figure out which ones are those. And then from there, for those that don't necessarily imply bijective, sorry, did I say surjective? I meant bijective. Find the ones that represent bijective. And then for those that don't, figure out which ones that remain represent injective linear transformations, which one represents surjective. So we just want to sort these 9 into those 3 categories. Which ones tell me just injective, which ones tell me just surjective, and which ones tell me that my linear transformation is fully bijective. All right, so we've hopefully convinced ourselves, or you've convinced yourself, that if we want a linear transformation to be bijective, if we want it to be invertible, if we want there to be able to be another linear transformation that does exactly the opposite of what our original one does, then that needs to be a linear transformation. I would say this is probably the most important item up here on top. It needs to be a linear transformation where ax equals b has a unique solution for all values of b that we could possibly choose. I'm going to share my screen so it's a little easier to see. So we need ax equals b to have a unique solution for all right-hand sides that we could possibly put in there. Because in the event that ax equals b has a unique solution for all b, that means that we can set x, the solution, equal to some other linear transformation, we're going to call it A inverse, applied to the right-hand side b. Right? In other words, we will hopefully, by the end of our first act in class today, be able to figure out how to determine a matrix, A inverse, which is exactly the inverse, or the matrix of the inverse transformation that undoes whatever A does. And then we can use that linear transformation, that matrix rather, to solve the matrix equation AX equals B. So In particular, I guess what I mean to say is the following. That if it's the case that we have a linear transformation T with standard matrix A such that AX is equal to B, and if AX equals B has a unique solution, no matter what A that we decide to put, or sorry, no matter what B we put on the right-hand side. Sorry, I'm mistyping stuff once again. So if AX equals B has a unique solution, then what we'd like to be able to do is just take both sides of this equation and multiply it by a new matrix that we're going to call A inverse. So A inverse times AX is going to equal A inverse times B. So I'm just multiplying on the left-hand side of both expressions on the left and right-hand sides of my equation by this matrix, this fictive matrix that we're going to learn how to calculate today called A inverse. And the idea is that when I multiply the inverse matrix, A inverse, by the original matrix A, of which it is the inverse, what I should get out of that is cancellation. I should get that A to go away. In other words, what I should get out of that operation is I should get an identity matrix, a matrix which does nothing to whatever input that we give it, a matrix which does not alter any vector that it multiplies. And so if I can find such a matrix, then that matrix will be useful for solving this matrix equation, because we'll get IX equals A inverse B. And since IX and I is the identity transformation here, the identity matrix, that just means that the left-hand side will be X equals A inverse B. Right? So if I can find an inverse matrix, A inverse, then this is what it's going to be useful for. I'm going to be able to multiply both sides of my equation by A inverse so that I can then solve the equation without having to do the usual sort of rigmarole that we do when we solve a matrix equation. And the idea is that, yes, solving any linear system of equations probably involves things like row operations to find the reduced row echelon form of something. But what the inverse of a matrix is going to allow us to do is to do that row reduction just once, to find the inverse matrix of A inverse, and then use that inverse matrix to then just do matrix multiplication against whatever right-hand side that we want to. So I can solve a bunch of different linear systems with different right-hand sides but the same left-hand sides if I have the inverse matrix representing the inverse of the linear transformation that defines the left-hand side. So this is where we're going with the next few things that we do today.